Okay. Hello everybody. Welcome to the next in the series of CERIAS seminar talks for spring semester 2017. So today we have again somebody from local. We have Yang Kwan from Computer Science Department. He's a PhD student here in Computer Science Department, working with Dangyong Zhu and Jiang Yu Zhang. And he typically works on system security. In particular, he's interested in using static analysis and tools which are coming from the software security, using that to find flaws and so overcoming the issues that we see typically in the system security. Today, he's going to talk about A2C, their a new project, which next week is going to appear at NDSS, one of the top tier conferences in security. And he agreed to give a talk about that before moving on to there. So, please.
Thank you. Thank you, and good afternoon. My name is Yong Kwon, and today I'm going to present A2C Disrupting Exploit Executions via Input Perturbation. This is a joint work with Purdue University and University of Georgia. So this winter, we had quite a nice winter, but in the securities, the weather is quite bad. We have so many vulnerabilities every day coming up. So essentially, we are living in a world of vulnerabilities. Just to name a few: buffer overflow, integer overflow, ROP, use after free, heap spring type confusion. There are so many attacks and so different ways to break the systems. But we shouldn't be that depressed because we have also good guys. There are so many protections too. We have so many antivirus systems, anti-malware softwares, and also from research communities, we have bound checker, CFI, DFI, and a lot of shellcode detection techniques, and ASLR. But here the problem is whether all these protections, now we are safe to use our computers. Definitely we will know the answer is not great. So we try to ask the question why? Why all these were not enough? So we analyze all these existing techniques. We come up with the answers to this question. So first, we find out that a lot of great protections, they have so many overheads, so we cannot just simply apply these protections. And the second reason is there are attack defenses that is specific to attack surfaces. So then we always know that attackers always find a way to break and avoid, circumvent these attack-specific defenses. And later, we also find that there are simply too large attack surfaces. Even though we prevent all the known attacks, we see that attackers always come up with a new idea to attack the system. So we say preventing known method may not last long. So naturally, these limitations of the existing systems lead us to have a new goal for our solution. So first, we want to have low overhead so that it can be practical. And the second one is we need to have a general protection. So we should not rely on any specific attack method to come up with a protection. So that with our system, we can potentially prevent a new attack method, which we don't even know now. And also, we want to be complementary because even though we are doing really hard, one simple system cannot prevent everything. So we want to prevent the system with other great protection. So the compatibility is our major goal. So we were thinking how we can come up with a solution with these very nice goals. And we started from analyzing a bunch of attacks in detail. And we find that in most attacks, attackers need to inject malicious payload, which they want to execute some of the sequence of operation. And we find by analyzing a lot of exploits, they are very fragile. Let me show you an example. Here we have an attacker and a program. And we find that most time they send first malicious input to trigger some vulnerability to break the software. And then once they trigger that exploit, trigger that vulnerability, they later send a payload, which is a set of operation they want to execute. For example, they want to open a network like a port so that they can connect them later, execute some malicious commands. Then we analyze this payload. Here is an example of the payload. On the left side is the hex code of this payload. On the right side, it is a instruction representation of this hex code. Essentially, these like hex code numbers, when you put into the computer, the CPU will see this instruction and do this command execution. So as we told that these payloads are so fragile, so even very little computation on this one, any mutation on this one, will break the semantics of this payload very completely. So here we apply XOR with AA. Then this is the result. Here you see like the first number 31 becomes 9B, and all the following numbers are changed. More importantly, you see on the right side, when the CPU sees this changed payload, it will see totally different instructions. So you see this payload is totally broken, and attackers cannot achieve their goals, what they intended first. So we built a system on top of this observation. Here is the high-level idea of our system. The program execution first starts with the inputs, and whenever we get inputs, we encode so that we get the encoded input. And when the program, and then the program will feed this encoded input. And when an attacker wants to execute their exploit, the payload is already encoded as we just saw in the previous slide, so the attack will fail. But this, you may have some question that what if they want to actually read the input and process something? So when the program execute a benign request, then we actually decode the inputs for that request, and then the program behave correctly. So because I just show you how we break the exploit, now I want to explain how we guarantee the benign execution is correct. So let me start with a simple input. It's a HTTP request with the post, and the path of this request is index.php, and there is a HTTP version specified this request. And before it gets read by the program, we first encode the input. So here we see I just do a simple minus. You see that like a P becomes O because P minus 1 in ASCII code is O. And all the following inputs are we just apply all the minus 1 operation on each byte. And the web server gets this input, and of course they want to parse and process input to generate outputs. Then we will do decoding for this web server. So when it wants to do some operations on it, we first take the encoded input, and when it wants to understand what's the command of this HTTP request, then they want to read the first 4 bytes of the request. Then we just take the 4 bytes and decode and give it back to the web server. So the web server can operate correctly. And it does for path, also for the version of the HTTP protocol. Now it gets all the correct inputs and produce correct outputs, even though we encode these inputs. So maybe naturally you may have some question, because we definitely decode some inputs here. And the question may be why the payloads are not decoded, even though some inputs are decoded for the P9 execution. So here is our answer. So the first thing is we actually decode based on the program's intention. Means that we respect the program's original intention of how they use the data. So we statically analyze the program and decode when the inputs are used by the program as the intended data. So you may think of there is no program, I mean, it's quite strong, but there's not much program that takes the input from the outside and try to cast this input as an instruction of the CPU and just execute. That sounds like a backdoor. So that also echoes our second point. These malicious payloads are actually not supposed to be executed by the original program. So what we do is we do not put decoding logics for this unintended execution, but we do decode for intended program execution. So all these 2 points actually came from an assumption that inputs should be data, not the code. So A2C, our system, allows inputs to be accessed as intended types of data, but it will break the code execution, which is unintended types of data, when it gets injected and exploited. So let me explain our system, its overview. So we first get the original program, and then we do static program analysis. The program analysis part consists of 2 parts. One is constraint solving and a static analysis. This one is quite complex. We will get into the detail very soon. So that's why we use constraint solver, which is G3 from Microsoft. And during the static analysis, we use LLVM. And then after this program analysis part, we get the instrumented program, has encoding and decoding functions. And then we also need to have the runtime support to execute these encoding and decoding functions. So let's start from static analysis, constraint solving part of the program analysis. We first need to answer when to decode and encode. Maybe the first question is a little bit simple. When to encode is fairly simple. We just say encode any incoming untrusted sources at library level. For example, if a program receives some untrusted buffer from outside, from network, then we just encode everything. If the program reads some untrusted files, we also encode everything. But the problem is when to decode. Intuitively, we can say we can decode when the encoded values are used. But we soon encounter this question. Programs take the input and process and then do some computation and then process outputs. Then if the program do some computation on these values, then it generates new values. Do we need to encode these values again or not? So this is actually fairly hard question to answer. So to answer this question, we first analyze the program and what they are really doing. Here is a small example that a program takes input, do some computation, and then generate outputs. Usually programs takes input, sometimes it copies here and there around because it needs to fragment inputs for different purposes. And sometimes program convert some of the characters into another type of characters. For example, some programs take ASCII code and convert it to the Unicode or vice versa. And the other types of operations like read and compare, essentially this one is a common operations in the parsing. So you first read the input and then have a predicate like if statement and then do something depending on the input. And also a lot of programs do like cast the inputs and do a lot of computation, for example, encryption, like mathematical programs. But in our context, because we are assuming that inputs could be malicious, we need to think about if we decode in these kind of operation, whether this is safe. Definitely the first one, copy operation, is not safe because copy doesn't change anything. So if we decode operation at copy operations, then essentially we are helping the attackers. We just get the input, encode it, and decode at the right time. But the conversion is a little bit difficult to answer because there are quite simple conversions, but also there are quite complex conversions. Actually, there is papers, like a lot of people thought that Unicode can break a lot of shellcode, because when you think about the Unicode always, not always, but for English letters, you need to always have zeros in every other bytes. People think that it will break a lot of shellcode, but there is also a lot of papers on it saying that with these kind of restrictions on numbers, you can still generate useful shellcode. So this one is quite difficult to answer. So let's move on. And there is a read and parse, a read and compare, which is parse. This one is fairly simple to say, because when they compare, actually they made a small copy of big chunk of the buffer, and then they compare, and then after comparison, soon they dispose the data. So we are saying this is safe to decode. So we have quick answer here. And also the computation. This is also similar case of the conversion. There are simple computation that we may see it as a copy, or there are very complex computation, which is hard to know whether it's safe to decode or not. So essentially, now we focus on these two complex cases, and we conclude that answer this question is essentially we answer the question of can attacker control the result after computation. For example, if the attacker send A, and after the computation they get X, and if attackers send B, and after the computation they get Y, that means that if attacker knows if A will get result of X, if B get Y, then he will prepare their shellcode beforehand so that even after the computation, their shellcode will get the right format. So in this case, we think that this computation is not safe to decode, because as you can see, after the computation, attackers still have control over the data. But this case, if attacker send A and it gets 1, if attacker send B, it also gets 1. No matter you send, you get always 1. In this case, pretty much we can say this is safe, because even though attacker knows the operation, attacker may not leverage this one to construct, because all attacker can have is just single number 1. So the problem is, even though there were two examples, we don't know, given a computation, we don't know which one is the case. So we're not sure, so then we need to ask somebody. So we try to ask the constraint solver to answer this question. Constraint solver is essentially a system you give a lot of conditions and ask them whether this condition is satisfied or not. Then they will do a bunch of computation and give you an answer. So here is a small program example that we want to know whether this computation is controllable or not. So you see M7 and IMG and MPR. IMG and MPR are the buffers that attacker can control, and M7 is the result of the computation. Computation is fairly simple. It's just IMG minus MPR and assign the result to the M7. Right. And one important thing is you need to notice that here M7 is unsigned int, which is 4 byte in most operating system, and IMG and MPR are unsigned short, which is 2 byte. So let's keep that in mind and see what happens. So to ask the constraint solver, we actually need to change the program language to the language that constraint solver can understand. So now we want to model this line 6, the computation, to the constraint solver language. This is an example of constraint solver language. The first, we model the computation. It's fairly simple. It's the same operations. It just does IMG minus MPR equals M7. And then we also give the range of the value. Remember that we have IMG and NPR are unsigned short, so we give the range of unsigned short, which is 0 to 65535. And then finally, we give the condition that whether the result M7 can be a payload. Here, the payload is an array of giant data, which we collected from a lot of different websites, which is essentially representing shellcode, rough gadgets, binary code, any possible random numbers. We collect these data from all kinds of different sources and made a 1.4 gigabyte a large payload pool, and we compare this data, concrete data, with this condition. And then we throw this operation to the constraint solver and wait for the answers, and constraint solver will say yes or no. Then we take this answer to answer the question. So essentially we use Microsoft G3 server, and we get the payload from internet like exploit database, metaexploit, sharestorm.org, and a lot of rough gadget tools we run on existing binaries. And also we generate a lot of random numbers using random generator. And also we decompile all existing Linux binaries on my computer and then put into the giant payload pool. So we ask the constraint solver, and if these are kind of answers that we can get from the constraint solver. The first one is SAT set, means that it's satisfiable. That means given that condition, an attacker can construct a payload through this computation. So in this case, obviously attackers have control. And the timeout means that we run constraint solvers, and the constraint solver tried to compute something, but it took too long time, and then we didn't get the answer in like a few minutes. So then we say it's a timeout, means that we actually don't know. So we take the conservative position, saying that maybe attacker can control. Unknown also means that constraint solver think that the computation is too complex, and some of the computation is not modeled in the constraint solver. So they say, I cannot solve this problem. So we also take the conservative position and say attacker may control because they don't know. But there are some cases that say that for sure, given that your payload pool, attackers cannot generate meaningful payload after this computation. So then in this case, they return unset. Then we say, okay, this is the safe computation. After this computation, the payload is totally broken. So now we can come back this. Sure.
Yeah. So my question is, but then there can be also some legitimate program where it will fail, right? You may not be able to, there will be a legitimate program, and then when you get them, basically you won't be able to make them working because you make the attacker's payload fail, right?
Right.
So there is also some false negative, or I don't know how you call it, that there are some legitimate code which are not attacker code and they won't succeed.
Actually, the answer is we guarantee the benign executions, correctness of the benign executions, so there's no breaking.
No, but there is a difference between benign and legitimate, right? Legitimate means everything which is possible. Even attacker's instructions are one which are possible in your system, right? But they are malicious, but they are still correct instructions, right? Or, I mean, how you make sure, what's not clear to me is how you make sure that, are you sure that there are some correct programs which will not fail in this way?
So this is actually computing decoding frontier is we want to know which computation is fairly complex enough so that attacker cannot gain the control over this one. But guaranteeing correct execution is more about how we can completely find because we blindly encode all the inputs, we need to find all the cases that inputs is used. So that one is done in the static analysis, which we covered a little bit later. This one is just, right. The first problem is actually, without this decoding frontier, what we can do is we just encode everything and decode everything. But that incurs a lot of overhead. So what we want to see was, because the inputs are going through some computation and then soon it will be difficult to exploit, then we are saying that we may not need to decode everywhere. We may just cut here and forget about all this complex computation to save the overhead and make it practical. So now we can come back to this question and can answer which one is safe, which one is not safe. So indeed, we find that some of the conversions are actually exploitable. If they know how they convert input to another values, they can prepare the payload in a very smart way so that after the conversion, it still has malicious payload. And also some simple computation, for example, like +1 multiplied by 2. These are, if attacker knows that computation beforehand, they also can prepare this payload so that it can survive after the computation. But we also find certain complex computations. After the computation, they have no access to generate some meaningful things. So here we have 3 exploitable, 2 fairly safe. So then we define it as a decoding frontier. Decoding frontier is essentially a computation that is fairly complex enough so that after this computation, attackers lost their control. So we find this decoding frontier using a constraint solver. And before this decoding frontier, we define the program space before this decoding frontier as an exploitable space, meaning that in this space, still attacker has much of control. And after this decoding frontier, we say program space, data in this space is fairly safe. So it's fine to decode and let it go. So now using all the answers from a constraint solver, we try to enforce our encoding and decoding scheme using static analysis. So we use LLVM, and the first question here is how we come up with decoding and encoding sets. Essentially means the places we want to decode, the places we want to encode. So as we covered previously, encoding set is a little bit simple. So we just encode every incoming untrusted sources at the library calls, for example, like receive from networks, read from untrusted files. And the decoding set, here we have a little bit clear answer that we decode whenever encoded values are used so that it will not break any legitimate functionality. And here we have one more further optimization is that we can decode inputs permanently at the decoding frontier. So after the decoding frontier, the execution is exactly the same the original program. We don't interfere any execution beyond the decoding frontier. So we use context, flow, and field-sensitive static analysis, which is very complex, to finding these decoding and encoding sets. So this guarantee benign execution and legitimate inputs will be processed correctly without causing any crashes. So let me explain how we instrument. We have this little program. It first receives some input from untrusted network. So there is an untrusted buffer will hold network data. And later we have a predicate that compare a contents of the buffer with the constant. And later we also have mem_compare function with this buffer. So first, right after it gets data from the network, we just encode the buffer. And the second one, when it compared, which is used by the program, we decode this exact buffer and then the computation with this constant will be succeed. And also, we do decoding at memcopy. So this will make the legitimate execution correctly. But we find a problem of just enforcing that things. Here is another example. We have one more statement within the predicate, which is memcopy. And what it does is put the constant into the untrusted buffer. So now we see what happens in here if we enforce our instrumentation. Here at the last line, the memcompare, we can see that this untrusted buffer actually comes from this receive from the network or this constant. So then let's think about what happened. So if we just decode untrusted buffer like blindly, then it will break the functionality when it has the constant string. Because constant string is not encoded, if we decode it, then it will have some weird values, and then the comparison will result different outcomes. But if we not decode this untrusted buffer, then it will break the value. It will break the program when the value is from receive. So here, our answer is we also encode the constant. So then now we can see that decoding blindly untrusted buffer will not break in any context. So this is how we will change our instrumentation. So we encode the constant in the memcopy. So in any context, untrusted buffer is always encoded. So now we come back to these basic questions that how we know all the encoding sets, all the decoding sets. So now we have more precise answers. We encode in incoming all untrusted incoming sources and library calls. And we also encode all the constant that can be written to any of already encoded buffers. And the decoding is the same answer. We decode when the encoded values are used. And one more optimization is we can decode permanently at the decoding frontier. So now I will show a little example of how we prevent ROP attacks. Essentially, ROP attacks is you corrupt the stacks and you corrupt the return address in the stack so that after it's exploited, then your control flow will go somewhere that attacker wants to go. So here we have a local variable. The size is 255. And there is a loop. And within the loop, there is a function that returns a string. And this string is, which is TMP, can be controlled by the attacker. And as you can see, right next line, we have a predicate, and it's used, it compares with the constant, so that to guarantee the correct execution, we decode here. And the next line is like strcat, means that concatenation of the string. Because this one is copy operation, we do not decode the TMP. And now we see what happens when it is exploited. Here is the ROP gadget that is injected into the system. Essentially, ROP gadget is an address that points to somewhere in your program that holds some meaningful instruction and as well as the return instruction. So we can see here the first ROP gadget points to a move instruction, and also return instruction is just followed. And there is another ROP gadget, another move instruction, and also return. So simply, we also do XOR operation on this guy, and then we get this. As you can see, the addresses is totally different, and it doesn't even point to valid addresses. So as soon as this one is exploited and try to execute this ROP gadget, it will just jump to somewhere random addresses and will fail, will crash the program. So now I will show some of the evaluation result. And this is the performance graph of our A2C. And we evaluate first 18 vulnerable applications, and we use fairly large inputs to test. And as you can see here, we have around like 6.6% of the overhead. And some of the program we have a little bit more overhead, close to 10%, which is like Apache or some XML parsers. These applications that has a lot of intense operation on inputs, because we decode more, it has a little bit more overhead. And this is the performance evaluation from the spec 2006. We get a little bit worse. We have around like 8% of the overhead. And there's one program which is like over 14, is a Perturbation. So we found that if the program actually used input all over its execution, then it actually disrupts much more like computation during the whole execution. And we also see some of the programs like MCF or Leap Quantum. These are very fast and then we analyze why, and we saw that these programs, first they read the input and they transform all of them into some primitive values, and then later they do a whole lot of computation without accessing original inputs at all. So essentially they have very like a thin layer of processing inputs and converting inputs so that attacker cannot exploit like a very few steps of the execution, and then whole other executions are like just pure computation after the input processing. And we also evaluate effectiveness of our tool. So we tested 23 different exploits on 18 programs, and we prepare 100 payloads. 50 is a shellcode, 50 is our rough gadget for each program. And you run and see what happens. And we just apply XOR with AA on this malicious payload, and we found that for the shellcode, which is a sequence of the hex code representing these x86 instructions, for these kind of payloads, we see that after our computation, after our mutation, only 3 or 4 instructions can be executed. But something very important to say is that even though they can execute 3 or 4 instructions, these are very different from what they are like, what the attacker really wants to execute. As we saw in the first few slides, we saw that the first one was XOR EAX. That's what the attacker wants to execute. But after the mutation, we see like F weight about the floating point computation, which attacker has no idea what they want to do. So, and also we evaluate a bunch of rough gadgets, and we see only 0.1 average number of rough gadgets are executed. And this is the sure. Sure.
Yeah. So in this, you are doing XOR with with A hex. Is there any particular reason? Because if you are fixing that value, then attacker knows that this is a George value you are using, and they can exploit that.
Sure. This I just pick X like a AA just for the for the sake of presentation. Actually, we are having a lot of different keys, and essentially we are using like one-time pad encoding. So we prepare bunch of one-time pad encoding keys before the execution, and then during the runtime, actually we pick randomly one of them. So actually we will also cover at later slides as that was actually right, quite a big problem, right, big critical question for this paper for a long time. So here is the evaluation on our decoding frontier computation. Right, we log all the decoding frontier computation from the constraint solvers, and then we found that among all the tested computations using constraint solver, 71% that we questioned were indeed a decoding frontier. Means that in the programs, actually, we have more complex computations so that we can forget about the security after this computation. And only 29% is controllable, so that means that we need to track the inputs further at that point to see real decoding frontier. So this echoes our assumptions that exploit space is quite small. So it means that inputs are quickly parsed and do not usually propagate deeply into a program. So because exploit space is not huge, our performance is quite not bad, quite good. We achieve quite good overhead. So here is some discussions on our limitation. So we can also think about attacks in post-exploit spaces, even though I argue a lot about after decoding frontier is safe, we are fine. But because we are using the payload pools that we collected here and there, and also because we are using this large pool of payload we collected, if an attacker come up with a very smart way to very different from what we have seen, how they the way of constructing the shellcode, then maybe our constraint solver computation is incorrect. And also, it is when we are testing of 16 bytes because we think that is fairly small size of the shellcode. But if attacker can construct very powerful attacks less than 16 byte, we may be in trouble. And the other one is just the question asked is about the memory disclosure. So let's say if an attacker can access all my memory data, and they can even know what I'm doing, they can even know what kind of encoding key, what I have used. For example, by leaking the previous buffer encoded several times, maybe you know what you can infer what kind of key that I have used to encode the buffer, because attacker knows what data they sent it, and then attacker also can now see how it is encoded. So the thing is, because we are using a different dictionary, different encoding key every time we get a new input, knowing the previous encoding key does not help you to attack next time, because you don't know what kind of key we were going to pick. So we have a lot of related works. It has a bunch of CFI these several years, and also malicious payload detections, a lot of address randomization, and a lot of bounds checking. And these are all great tools. The key point of our solution is we are trying to attack a different perspective. For example, CFI try to focus on the control flow. They want to enforce whether the program goes the right way. And malware payload detection, they use machine learning and try to see the patterns. And randomization, they need to disrupt these address spaces so that if attacker has some strong assumption on the layout, then they cannot, with this address randomization, they cannot prepare the payload. We are essentially trying to attack on the different perspective, which is from the data. So what we are doing is we encode all the inputs and then try to decode at when the program is legitimately want to use these guys, and then we decode. But we think that most of attacks happens they break the assumption, break the intention of the original program. So we are attacking that point. So here is the conclusion of our talk. Is we present A2C, which is which provides a general protection against a wide spectrum of payload injection attacks. Even maybe we can prevent some unknown attack surfaces. And the way we do is we encode all inputs from untrusted sources, and then we decode right before when they are used, so that we can correctly guarantee the executions. But we break malicious payload because it does not go where the program intended to use. And we also prevent payload injection with a fairly low overhead, around 7%. Thanks for the listening, and this is the end of the talk. And if you have any questions, welcome. Yeah.
Questions? Okay. So let me start then, continuing from what he asked, and you actually, that's what I was alluding to. So you assume that you keep on changing keys, but for the one-time pad, the key challenge is that the more you use it, you should not reuse the key. So there are two aspects. What if somebody decides to reverse engineer your program? Mm-hmm. Then they will be able to know what is the next key that you're going to use. Mm-hmm. Okay, let's say you assume that adversary has access to the copy of the program. And then they can reverse engineer possibly to find out what is the next key that's getting used. Okay. And the second thing is, even in that, let's say if that's not allowed to the adversary, you are going to, there is only this much keys that you can store. After, let's say, using, running this program for 1 million times, then you are exhausted the key space that is available to you, and you're going to use back again the key that is used for the first time.
That's true.
So, any thoughts on both any of these questions?
Right. I would say, like, in practice, it's difficult to actually predict, like, a random generator, how they give the random, how the random generator returns numbers. Maybe, maybe we can use better random generator so that it will make the, guessing the next input difficult. And the another one is because we have, ideally we can have the infinite number of one-time pad, but of course in practice it's impossible. So we need to store some a concrete number of things. So maybe I think it's a good way to enhance the security of, in this case, is maybe we can restart the program or time to time, so that after a few hours maybe you can refresh your all the one-time pad, so that let's say an attacker gets some idea in this morning, and they have analyzed and they come up with a nice idea and try to attack on the afternoon, and then now they see a whole different system. I think that one can be easily done.
All right. So let's thanks again.